Let's think about that time once again. Last time we were talking about the brain and some of the things it's doing, and we're just about done talking about that. We will then move on to the autonomic system, the stuff that's going on in the background, and the sensations, which will round out the end of the semester. Speaking of the end of the semester, it's less than 2 weeks away. 10 days actually. So again, it is coming up really soon, believe it or not. Please make sure that any assignments that you've not done are done no later than the last day of class. That is the last time that I will do this. You're about 11. But again, that whatever Monday that we do is the last day of class. Please make sure everything is turned in before that. That includes any of the physical body exercises, which some of you are quite a bit behind on. I'm not sure about in this class. People are actually showing up. But the physical bodies, the lab assignments, physio-ex. If you've not got anything in, by the way, everything is up to date on Brightspace. So if you see anything where you don't have a 4 or you missed a day or missed a 3, that means you didn't turn something in. So make sure you get everything. Every point counts. Having said that, continuing on, we have to talk a little bit about the limbic system. And, oh, by the way, don't know if I mentioned it or not, lab quiz should be showing up either today or tomorrow. Lab quiz will be showing up online. Again, the due date for that will be the last day of class. So again, that should come out. Limbic system. The limbic system has everything to do with your emotions. Again, it is a number of centers here which happen to wrap around the diencephalon across here, including things like the hippocampus and the amygdala and the olfactory bulbs. And what, again, the limbic system is all about is highly involved in determining what your emotional state is. Are you happy, sad, angry? These are all controlled through centers of the limbic system. In addition to that, very much involved in memory formation, and especially memories that involve emotions. Strong emotional memories are going to be passing through the limbic system, and anything that's going to provoke those memories will typically have a strong emotional response associated with that. So again, very much involved in memory storage and retrieval, and because it does include the olfactory bulbs, central processing of smells. Smells run through the limbic system, which means you can get a strong emotional response to a smell, unlike you do for things like color. So certain smells can provoke a strong emotional memory, and again, that is going to be highly individualized. Exactly why this should be the case is not at all clear, but it probably has to do with pheromones. Pheromones are chemicals that are produced by certain animals to allow them to communicate with each other. A lot of insects, for mating purposes, will send out these chemicals to attract, particularly the females, to send them out, and then all the males come looking for it. Cats, dogs do the same thing. When your dog is sniffing the tree, he's sniffing for these pheromones to see if somebody else has been there recently. They care a lot more than possible than we do. As far as we can tell, humans don't do this. We do not appear to have, nobody has identified a human pheromone, and people have looked. But again, as far as we can tell, humans don't actually do this, but evolution working the way it does, we still have this strong association with our sense of smell. And that is the current guess as to why the olfactory bulbs and smells are processed through the same method that we process our emotions. But again, that's the limbic system. There's a number of centers in here surrounding the diencephalon. All right, having said that, any questions to this point? If not, let's go. There's the wrong button there. All right. In that case, now let's move on and talk about the other portion of the nervous system. We've been talking about the somatic nervous system, the stuff that you're aware of. We now need to talk about the autonomic system. We've seen this slide before, by the way. The autonomic system, that's the involuntary portion, the stuff you're not aware of. The things that your body does on the background, keeping track of things like your heart rate, your blood pressure, your breathing rate. These are all autonomic functions, pushing food through the GI tract. We don't think about that, it just goes on its own. Again, these are all autonomic functions. And the autonomic system is divided into two broad divisions, the sympathetic and the parasympathetic. The sympathetic division, that's your acute stress response. Something jumps out at you, your heart rate goes up, your breathing rate goes up, your pupils dilate, those are sympathetic responses. Also turns things down, the urinary system gets turned off, the digestive system gets turned off. Things that you need to fight off or run away from whatever is attacking you get turned on. Things that are not helpful get turned off by the sympathetic system. The parasympathetic division does the opposite. This is the rest and digest mode. This is your relaxation state. That includes things like lowering your blood pressure, lowering your heart rate, lowering your ventilation rate, increasing digestion, increasing urination, the urinary system. These are all parasympathetic responses. So again, they complement each other. One turns things up, the other turns things down. Exactly which way it goes depends on what how useful it is to you if you're trying to run away from some danger. And they all have the same basic pathways coming out of the brain. Now, as you will recall, when we're talking about the motor pathways coming out, we had an upper motor neuron and a lower motor neuron. It required two neurons to get us from the brain out to the body. Here in the autonomic system, it takes three. It takes three neurons. We have one starting up here in the brain, bringing us down into the spinal cord. Then we have one neuron that takes us out to a ganglion out in the body, and that is known as the preganglionic neuron. So we have two peripheral neurons here. We have what's called a preganglionic neuron, and that preganglionic neuron starts in the central nervous system, the spinal cord, or the brain, depending on where it's at, and goes out to a ganglion out in the body. Again, a ganglion is a patch of cell bodies neuronal cell bodies outside of the central nervous system. In other words, it's a piece of gray matter. So gray matter outside the central nervous system is called a ganglion. And this is where we're going to have synapses occur. And again, this preganglionic neuron here originates, it has a cell body here inside the central nervous system, and goes out to the axon and then extends out to a ganglion. This one will always be myelinated. So the preganglionic neuron is always myelinated, meaning it is fast. So the preganglionic neuron will be fast. It will then synapse with a postganglionic neuron, which will go from the ganglion out to the organ of interest. The heart, the lungs, whatever it happens to be. So again, we have a preganglionic neuron and a postganglionic neuron. Whereas in the motor system, we simply had one motor neuron going all the way out, and it was myelinated. The postganglionic neuron, the second one here, is always unmyelinated. It is unmyelinated, meaning relatively slow. Slow compared to myelinated ones. It's still a neuron system. But again, we have a preganglionic neuron and a postganglionic neuron coming out from the spinal cord out to wherever it is that we're trying to guess. All right, so that will be true for both the sympathetic and the parasympathetic systems. We will have a pre and a postganglionic neuron hanging out here. So let's take a look now at the sympathetic system, and it looks something like this. As it turns out, the sympathetic and parasympathetic systems are anatomically distinct from each other. And as you can see here, this one is also known as the thoracolumbar division because it comes out of the middle of the spinal cord. The thoracic and the lumbar nerves are contributing here to the sympathetic division here. And as you can see, we have a preganglionic neuron that is coming out, and it's immediately running into a ganglion. These are what are known as the sympathetic trunk ganglia. So again, that preganglionic neuron, which is short, it's myelinated, and goes straight out to a ganglion. These are known as the sympathetic trunk ganglia, and they run right up and down either side of the spine. So it exits the spinal cord, comes out of the vertebral column, and immediately hits a ganglion. So we have a very short preganglionic neuron. That'll be a very short preganglionic neuron. The postganglionic neuron, going out to say the heart here, is then going to be relatively long. We'll then have a long postganglionic neuron. So again, the preganglionic neuron in this case is going to be short. The postganglionic neuron will be long. Again, the preganglionic neuron is myelinated. The postganglionic neuron is unmyelinated, meaning most of the distance here from the spinal cord out to the organ of interest is unmyelinated. In other words, it's fairly slow, relatively slow. So again, that is what the sympathetic division looks like. Again, this is coming out of the middle of the spinal cord, between the enlargements. You'll recall that the enlargements, that's where the somatic system came out into those plexus. So this is coming out between the enlargements. And that is what the sympathetic division looks like. Now, what does the sympathetic division do? Well, among other things, it increases your level of alertness and activates the RAS. Makes you alert, tells you, hey, there's danger out there. And increases your muscle tone, getting you ready to either fight off or run away from whatever it is that is attacking you. It mobilizes energy reserves, enabling you to make more ATP. So we're going to release glucose from the intracellular stores and allow us to use that energy to, again, make ATP with. It's going to increase our heart rate and our blood pressure. You don't know this yet. But your blood pressure and your heart rate are directly related to each other. If you increase your heart rate, you automatically increase your blood pressure. There are two things that go into determine your blood pressure, and one of them is your heart rate. So again, anytime you increase heart rate, you increase your blood pressure. But again, it increases those, getting more blood out to your organs. Increases your breathing rate, getting more oxygen inside of you to again make more ATP, getting you ready to run away or fight off whatever is attacking you. And this one's a little less obvious, but it reduces your pain sensitivity. Again, if you're getting into a fight, you know it's going to hurt. You don't need to be reminded of it. So it turns off your pain sensitivity and increases feelings of euphoria. This is where the runner's high comes from. When you start exercising, start running, that puts stress on the body, and that activates the sympathetic nervous system. And that increases feelings of euphoria. So if it's a relatively mild kind of stressor out there like exercise, it makes you feel better. It makes you feel better. Why? So that you keep fighting off whatever it is that is attacking you. To encourage you not to give up. So again, it reduces your pain sensitivity, increases your feeling of euphoria, keeps you happier, and that's why it feels better when you exercise. But again, keeping you, encouraging you to continue fighting or running away from whatever it is that is attacking you. It also dilates the pupils. This one's less obvious. And exactly why it should dilate the pupils, I don't know, it just does. And causes ejaculation in the male sexual response. So again, these are all sympathetic division things that are done by the sympathetic division. All right, so that's the fight or flight response. Again, your sympathetic responses, things that are helpful if you're trying to run away or fight off something that is attacking you. The parasympathetic system, on the other hand, comes off the top and bottom. So this is known as craniosacral. Cranial because some of the cranial nerves are involved in this, sacral because it comes off the bottom down here in the sacral region. So the craniosacral division here is the parasympathetic division. And in this case, once again, we have a preganglionic neuron coming out to a ganglion and a postganglionic neuron hanging out here. But now that ganglion is out here, right next to, or in many cases, within the organ of interest. So most of the distance here is preganglionic. So we have a long preganglionic neuron. And that preganglionic neuron, again, is myelinated. The postganglionic neuron is short and unmyelinated. So again, the ganglion is out here next to the organ, in some cases in the organ. So most of the distance here is myelinated. This is in contrast to the sympathetic system where the ganglion was next to the spine, where most of the distance was unmyelinated. So which is faster, the sympathetic or the parasympathetic response?
Parasympathetic?
The parasympathetic response because it's mainly myelinated. So if we were to stimulate you with both a sympathetic and a parasympathetic stimulation at the same time, which one is your body going to pay attention to most?
Parasympathetic?
The sympathetic system. Why? Because you pay attention to the last signal that you get. So if we give them both at the same time, the parasympathetic gets there first and then is overridden by the sympathetic division because it gets there second. We pay attention to the last signal that we get. So again, if you get both at the same time, you pay more attention to the sympathetic because it arrives later. It's the last signal that you got. So again, the sympathetic division is capable of overriding the parasympathetic division. And again, that's what you would want. If you had to choose whether or not to make the mistake of being too alert or not alert enough, which one would you want? Well, if something's attacking you, you want to know about it. So evolutionary makes a whole lot more sense for the sympathetic to win out. And it does. So again, the sympathetic division can override the parasympathetic division because it comes after. It comes after. All right, so that is where the parasympathetic division comes off, top and bottom. Top and bottom. Again, in the middle here, that's where the sympathetic division came out. And between them, in the enlargements, that's where the somatic system comes out at. So again, different portions of the nervous system come out at different portions of the spinal cord. So what does the parasympathetic division do? Well, it does essentially the opposite of what the sympathetic division was doing. It reduces your heart rate, reduces your blood pressure. Again, the two are directly linked. Reduces your ventilation, your breathing rate. Stimulates digestion and absorption. Again, if you're running away from something, that's not the time to be eating. When you're sitting around relaxing, that's the time to digest your food. So again, it stimulates digestion here. By which I mean it increases salivation. Salivation is a parasympathetic response. As is secretion of digestive juices, motility of the GI tract. All these things involved with digestion are stimulated by the parasympathetic division, and we're now going to store energy as opposed to releasing the energy. So we're going to pick up any glucose and store it for later use. Defecation and urination are also parasympathetic responses. Again, when you're running away from a tiger, that's not the time to go to the bathroom. When you're not being chased by something, that's when it's okay to stop and take a bathroom break. Yes.
So silly question. So when somebody's really scared, sometimes they'll wet themselves with their pants or whatever. How does that play into that?
That's a somatic response. First of all, we'll talk about this next semester when we talk about urination. But the decision whether or not to urinate, there are two sphincters involved. One is voluntary, and if you release that one, and it's the other one. So again, the inner sphincter has already been opened, meaning your bladder's full. All right, so that's defecation, urination. Constriction of the pupils. Again, dilation is sympathetic, constriction of the pupils is parasympathetic. Again, they go in opposite directions. Sexual arousal, again, is a parasympathetic response. Again, when you're being chased by a tiger, that's not the time to think about sex. When you're not doing anything else, that's when you do that. So again, these are things that are done by the parasympathetic division here. Again, things that are good when you're not being chased by anything or not fighting something off. So that's the autonomic responses here, sympathetic and parasympathetic divisions here. We now need to move on and talk about how we learn things and talk about memory. Memories are not all the same. We have a number of different kinds of memories that we produce. Some of them are memories of how to actually do something, and those are known as motor memories. That is how to actually do things like walk. You were not born knowing how to walk. You had to learn how to do it over time. You had to learn how to pick things up, put them down. These are motor memories. These are things that you learn to do over time. Again, infants are pretty helpless because they don't have any of these motor memories out. But again, we do learn a lot of these very quickly. Motor memories are memories of how to do something. Tying your shoes is the classic example of a motor memory. If I ask you to tie your shoes, hopefully you all can. But if I ask you to tell me how to tie your shoes, that's much more difficult. So that is a motor memory. That is something you know how to do. We also have what are called, and sometimes we do these things so many times, they become reflexive. Meaning that you don't have to think about them anymore. They just happen. Again, these were things you had to learn to do, but you've repeated them so many times that your body just automatically does it. For instance, if you're driving down the road and something jumps out in front of your car, you slam on the brakes, even if you're in the passenger seat, right? We've all done that. That is a reflexive memory. That's a reflexive memory. Anytime I get out of the car, my car door gets locked, whether I want it to or not. Because again, I just automatically lock the door, and if I want to keep it unlocked, I have to keep reminding myself, don't lock the door, and it still ends up locked anyway. Back when we actually all carried real keys, I'd leave the keys in the car and you have to go find another set of keys. Now we have these wonderful pubs, so that doesn't happen anymore. Technology, good. Those are reflexive things that you do over and over and over until they become automatic. Then we have what are called explicit memories. And these are things that you can actually recall. You can think about, you can refine them, you can answer them on an exam. These are explicit memories. And explicit memories can be either abstract or declarative, things you can talk about. Your mother's maiden name, for instance. Who your kindergarten teacher was. Those are abstract or declarative memories. What's 2 plus 2? Abstract, declarative mean the same thing. Abstract. Some people say declarative, some people use abstract. Again, they mean the same thing. Or they can be episodic or procedural memories. Things you can do. Skills. Tying your shoelaces. That is an episodic or a procedural memory. So things that you can do, those are episodic or procedural. Things you can talk about, verbal memories, in other words, are abstract or declarative. So again, these are all different kinds of memories that we all have. Talk a little bit more about these explicit memories, the things you can actually recall at will. Some of them are said to be working memories. And this has to do with how long you actually remember it. Working memories are memories that you hold long enough to do the task at hand, and then you let them go. For instance, it's late at night, you're hungry, you decide to order a pizza. You go to your phone book, you look up a number, you dial it into your phone, and then 5 minutes later when you decide, I don't want those toppings, I want something else, you have to look up the number again. That's a working memory. For all of you who remember phones of dials. And phone books, I guess, too. But anyway. Those are working memories. Working memories are things that last only a few seconds, maybe a couple minutes, let you do whatever it is you're trying to do, and then you don't remember it anymore. And you have to repeat it. So again, the phone number said that you just looked up. Short-term memories last a bit longer. Minutes, maybe a day. Seconds to hours. These are short-term memories. For example, where you parked your car this morning. I hope you all remember where you parked your car. But if I ask you, where did you park 3 days ago, can you tell me?
Only if it
Probably
was
wasn't
here.
anywhere here because that was a Sunday. Again, what you had for breakfast this morning, you probably know. But if I ask what you had the last Tuesday, you probably don't. Unless you have the same thing every day. So again, those are short-term memories. Remember them for a little bit, but not very long. So again, and they're information that's not particularly important for you to keep. Then we have what are called long-term memories. Long-term memories will last days, years, decades, potentially forever. Long-term memories are things like your name. Chances are you're never going to forget it. Chances are you'll never be forgetting your name. Things like your mother's name, your house number. Things like these are long-term memories, everything you're learning in this course. Hopefully. Are long-term memories. Because it will come back up later for most of you. But anyway, long-term memories are things that you learn for a long period of time. And these different kinds of memories are stored differently. They are stored differently in the brain. And we know this, again, from people who have had accidents or strokes, who have brain damage, and they lose the ability to form certain kinds of memories. I have an aunt who had a stroke when she was 36, and over time has lost her ability to form short-term memories. She can't tell you what she did yesterday, but she can tell you every embarrassing story from when I was a child. Her long-term memories are fine, or they were, but she has trouble forming new ones. She can't remember things. And you have to constantly remind her where she's at, what we're doing. So again, we know that we form these memories differently because we can recall them, we lose them in different ways. Likewise, there are people out there who have no long-term memories, and everything is in the moment. So again, we know these things are going on out there. Short-term working memories appear to utilize existing neural circuits. In other words, they're software. They're not changing anything in your brain specifically, they're just changing how you actually use it. Long-term memories, on the other hand, appear to be hardwired in. Long-term memories require new protein synthesis, new neuronal growth, new synapses being activated. Those happen with long-term memories. So again, short-term memories, you use what's already there. Long-term memories, you build. You create new structures to keep those long-term memories going. So again, they are stored very differently. And the process of going from a short-term memory to a long-term memory, I think it's fairly obvious all of our memories start as short-term. Moving them into long-term is called consolidation. Consolidation is the creation of a long-term memory from a short-term memory. And it appears to occur when you are asleep. So again, when you're studying for your exams, get a good night's sleep. That will help you to remember things. Naps are also great. So again, consolidation, conversion of short-term memories into long-term memories appears to occur while you are sleeping. So again, staying up all night cramming for the exam is not a good idea. You're better off getting a good night's sleep, which I know is really hard to do the day before an exam. But bear that in mind over the next week or so. And again, different types of memories are stored differently in different portions of the brain. And again, we know this from people who have had brain damage of one sort or another. So different memories are formed very differently. All right, so that's a little bit about memory. For more details, take a psychology course. Because again, that's really a psychological problem more than a physiological problem. We now need to talk about how we know some of these things are occurring. And we're going to talk a little bit about what is called an EEG. An EEG is an electroencephalogram. And what we do, this is very similar to what an EKG is, an electrocardiogram, where we're looking at the electrical activity in the heart. In this case, we're looking at the electrical activity in the brain. And when we're talking about electrical activity in the brain, what are we referring to? Say that louder. And with confidence. When we're talking about electrical activity, what are we talking about? Yes?
Brainwaves?
Say that again.
Brainwaves?
Well, brainwaves are what we're actually going to measure. But what is the thing that are the things that are going to result from this? What's the thing that's causing the brainwaves? Yes?
Brain activity.
What kind of activity? And we spend a lot of time talking about it.
Action potentials?
Action potentials. Action potentials. We're talking about action potentials here. Firing off axons with action potentials. We're measuring that. When we're talking electrical activity in the body, we're talking about action potentials. Please remember we're talking about action potentials. But anyways, as we measure these, under different conditions, we get different kinds of waves coming out. And as we take a look at these waves, a couple of words about waves in general. Waves can be described by two things. Number one, their amplitude, how tall are they? And 2, their frequency. How many beats per second? Beats per second is hertz, HZ, hertz. So when you see something in terms of megahertz or something like that, it's referring to the number of beats per second. So beats per second is frequency. And as you take a look at these different levels of different kinds of waves here, you can see some of them are relatively low frequency, some are much higher frequency, more beats or more beats. It doesn't show up very well on this particular slide, but there are differences in the amplitude on all of these as well. So there are differences in both amplitude and in frequency. And again, any wave can be described by its amplitude and its frequency. And what you're looking at here are the 4 kinds of brain waves that we can see: alpha, beta, theta, and delta. And for those of you who know your Greek alphabet, you will immediately recognize that these are not the first 4 letters of the Greek alphabet. The first 4 letters are alpha, beta, gamma, and delta. I don't know how theta is not in here. It's not even the fifth one. But anyway, it's alpha, beta, theta, and delta. And they're not in order. They're also not in order. Because as it turns out, your most alert state is beta. Beta is when you are awake and alert and looking around you. If your eyes are open, you are in beta. If your eyes are open and you're looking around, you are in a beta state. This has the lowest amplitude and the highest frequency, more than 13 hertz, more than 13 beats per second. More than 13 beats per second. So what we're seeing here, we're seeing axons firing off all around the brain in a non-synchronous way. So they're just all firing off at whatever rate they have been doing. So again, beta here, this is your most alert. You are awake, you're looking around, and you are active. So again, your eyes are open and active, and this is your most alert state, is beta. I don't know why they put it on the second line of the finger. It really should be the top line. If you're sitting around not doing much and just sort of hanging out with your eyes closed, that's alpha. Alpha is also an awake state. The amplitude is less than beta, and it's 8 to 13 hertz. It's a bit slower. And as we are slowing down, what we're seeing here is some of those. We're starting to see some synchronicity in the firing of the axons. So instead of them all just firing off, not really random, but separately, they're starting to sync up and starting to fire off at the same time, and they're starting to combine in the signals here. So again, here in alpha, we have a lower frequency, fewer beats per second, and it's also a bit taller. But that is when you are awake with your eyes closed. Again, anytime you open your eyes, you immediately go into beta. It takes a lot of brain activity to operate the brain. When you fall asleep, you drop into theta. Theta is a light sleep. This is a light sleep state. Again, it's even slower, 4 to 8 hertz, and a bit taller. But this is a light sleep state. Your deepest sleep is your delta wave. Delta waves have the highest amplitude and the slowest less than 4 hertz. And again, this is your deepest sleep. So high amplitude, slow waves. What we're seeing is waves of depolarization running across the brain here. So we're seeing a lot of synchronicity among those different axons when they're firing off. They're firing off at the same time. But again, that's what you see when you are out to the world. Those waves. So again, we have 2 wake states, alpha and beta. Theta and delta are your sleep states. All right, so these are different kinds of brain waves that we can measure from an EEG, and they give us a certain amount of information here. These days, you're more likely to put somebody into an MRI machine and just look more directly at it, see where they actually disappear. But EEGs still have their uses. Which means we're now getting ready to talk about sleep. And before we can talk about sleep, we need to talk about our biological rhythms. So what is a biological rhythm? It is something that occurs on a regularly repeating cycle. So something that occurs over and over and over again at some particular interval. The most famous of these are our wake-sleep cycles. We wake up in the morning, we fall asleep at night. Again, and we repeat it every single day. That is what is known as a circadian rhythm. Some of these biological rhythms are around a day in length. Some of them are shorter, some of them are much longer. Think about the female reproductive cycle, it's about 28 days. So again, that's a different kind of cycle here. Biological rhythms, we have lots of these biological rhythms, and some of them are said to be free running. Again, the classic example of a free running rhythm would be the menstrual cycle. It's not dependent on environmental cues. It doesn't matter if it's hot or cold out. It doesn't matter if it's light or dark. It goes at its own cycle. It just keeps running. Keeps running along. So it's independent of environmental cues. And those are said to be free running. Free running ones are independent of any environmental cues. Then we have what are called phase shift rhythms. And phase shift rhythms are reset by environmental cues. Most famous of these are the circadian rhythms. The circadian rhythms are the ones that happen on a daily basis. They go up and down on a daily basis. And they are reset every morning to the local conditions. So if you are sitting here, you wake up in the morning, you fall asleep at night, move to South Korea, which is about halfway around the world from us, it's about 12 hours off, will you continue to wake up at the same time? No, you're going to switch to when daylight there is. Because again, we humans have evolved to be active during the day. So we will switch and we'll change our rhythm to match the local conditions. These are phase shift rhythms. And again, the circadian ones are the most common, and they are reset specifically by light. Sunlight, particularly like the blue rays. So when you wake up in the morning, you see the sunlight, and that tells your body it's morning, regardless of where you may happen to be, or when night happened to fall the day before. So again, these phase shift rhythms will readjust pretty quickly to whatever the local conditions are. And again, the circadian rhythms repeat approximately every 24 hours. Circadian means around a day. So approximately every 24 hours, these will repeat. And there are a bunch of them. These are the most common of your biological rhythms, are the circadian ones. And they include things like your wake-sleep cycles. Various hormone secretions. Men also have a reproductive cycle, and it is a circadian rhythm. Testosterone levels go up in the morning, go up at night. They come down in the morning. So they're highest in the morning. They then rise up again at night. So again, that hormone secretion, thyroid hormone, comes out at different times of the day. There are lots of different hormones that are operating on the circadian rhythm. Body temperature. Your body temperature drops at night when you fall asleep. Wake up in the morning, it goes back up. So it does go up and down on a circadian rhythm as well. So hormones, body temperatures. Lots and lots of things that you can think about go up and down on a daily cycle. And the clock for all of this is something called the suprachiasmatic nucleus. The suprachiasmatic nucleus hangs out here in the hypothalamus. It's right here. It's called suprachiasmatic, superior, above, chiasmatic is right above the optic. This is the optic chiasm right above it. That's where the name comes from. I do not expect you to be able to label it. I don't expect you to be able to label it. But the suprachiasmatic nucleus, that's your body's clock. That's your clock. That's your internal clock. And it's in the hypothalamus, and it's controlling a whole bunch of things. It has inputs into lots of different areas, including the pineal gland. And so we have projections coming from the suprachiasmatic nucleus out to the pineal gland, where it will then produce melatonin every night. And that melatonin is required for your ability to sleep. How it is helping you to sleep, we don't really know. Again, the melatonin receptors have only recently been discovered, and for a long time we didn't even know where it was binding. But again, we have these melatonin receptors, and they are very important for your ability to sleep. If you don't produce melatonin at the right time, you have a very hard time falling asleep. But if we just give you melatonin, it doesn't put you to sleep. So melatonin is required for sleep, but it's not sufficient. There's something else going on too. And exactly how sleep works is not clear. How sleep works is not at all clear. But it's very important to us. But again, the suprachiasmatic nucleus, that's the biological clock telling you when to wake up, fall asleep, and do lots of other things. And it is reset every morning by sunlight. So again, light is the most important factor in resetting the suprachiasmatic nucleus on a daily basis. Specifically, light in the blue range. So again, the suprachiasmatic nucleus, that's the pacemaker, and it is reset to correspond with the local light and dark conditions. Specifically, it is light that is important in resetting the clock in the morning. So when you wake up in the morning, you see sunlight, and this light, by the way, is specifically light in the blue end of the spectrum. It's light in the blue end of the spectrum that is important for resetting the clock. Red light doesn't do it. Blue light is what is important for resetting the clock. Unfortunately, for our modern lives, this causes a bit of a problem. Because many things in our daily lives, things like computers, televisions, phones, all emit light preferentially in the blue end of the spectrum. Which means as long as you're looking at your phone, your body is being told it's day, and we should not be falling asleep. Fluorescent lights do the same thing, by the way. They're blue end of the range, yes.
Well, what do those blue filters that you can put over your
They
screen?
filter out the blue light
Okay.
to try and prevent this from occurring. So blue filters are there to try and filter out that light. That blue light is keeping you awake. If you want to get a good night's sleep, turn off your devices. Better idea, put them in another room. Because again, they ping and do make noises all night too. But again, if you want to get a good night's sleep, you need to turn off your device before you go to bed. Because that will keep you awake. Conversely, if you're working the night shift, what do you need to do? Make sure you get lots of light at night. And try and get as dark as you can during the day. Because again, we have evolved to be active during daylight, not at night. Again, this is a species-specific thing. Humans are active during the day, we're dying. Other animals like bats are active at night, so they do the opposite. But again, blue light is a problem for us, and that there's a lot of it out there these days, even when it's not day. So even at night. So again, by the way, if you do work the night shift, you have my sympathies. It's terrible. It's a terrible thing to do because they're out of sync with everybody else. And importantly, you want to turn the lights on. You want the lights on. And you want to get them off during the day so that you can get some sleep at some point. All right. So those are the environmental cues. Again, specifically blue light. Blue light is the most important factor. So, falling asleep. How do we do this? Well, number one, this is going to involve something known as the reticular activating system, which we mentioned previously. This determines your level of alertness. So the rest determines your level of alertness. And it contains both aminergic and cholinergic neurons. Aminergic neurons are ones that are based on the amines, norepinephrine, serotonin. These are aminergic. Cholinergic neurons produce acetylcholine. So we have two kinds of neurons here in the system that produce two different kinds of neurotransmitters. Using the aminergic neurons promotes arousal. It makes you alert and inhibits your ability to sleep. So if we want to fall asleep, we need to turn off the aminergic neurons here. These need to be turned off in order for us to fall asleep. So long as these are being activated, we're going to be alert. And again, the rest here, using those aminergic neurons, is going to keep you up. So we need to turn these off in order to fall asleep. Then when we fall asleep, the cholinergic neurons come into play, particularly during REM sleep. And we'll be talking about REM sleep in a minute. REM sleep is rapid eye movement sleep. This is your dream state. So when you are dreaming, that cholinergic pathway wakes up and becomes very active while you are dreaming. So again, we do have these two different pathways. One is for your being awake, the other is for when you are asleep. here in the RAS. And again, we've seen this slide before. The RAS gets inputs from your eyes, your ears, and various other locations, and has inputs throughout the rest of the brain, regulating your level of alertness. And sleep itself comes in two types. Non-REM sleep is the same. First of all, we have what is called REM sleep. REM stands for rapid eye movement, because during REM sleep, your eyes are moving around. Your eyes are sitting there and moving around. Hence, rapid eye movement sleep. And this is also known as paradoxical sleep. Why is it known as paradoxical sleep? Because during REM sleep, this is what your brain waves look like. This is what your brain waves look like during REM sleep. This is what your delta waves here, your deep sleep state. This is your awake state. Which one does REM sleep look like?
Awake.
It looks like your brain's awake. So your brain is acting like it's awake, but the rest of you is still asleep. That is why this is called paradoxical sleep. So your brain waves indicate that you are in fact very alert and very much awake, but you very clearly are not. So the EEG here looks like the alert state. It looks like your beta waves. And in addition to that, not only does it look alert, it's using a lot of oxygen. It's metabolically very active at this time. In fact, it is more active than when you're actually awake. The highest brain activity is when you are in REM sleep. So we have our highest levels of brain activity during REM sleep in terms of oxygen consumption. So oxygen consumption is elevated. And to supply that oxygen, the eyes, the heart, and the respiratory system are all turned on as well. So your heart rate goes up, your breathing rate goes up to make sure the brain is getting plenty of oxygen, plenty of nutrients going into there to support this high oxygen consumption during REM sleep. Your eyes are also active. Why that's important, we don't know. But again, your eyes are also very active at this point. Everything else, your brain, your eyes, your heart, the lungs, they're very active. Everything else is out. Everything else is completely paralyzed. Well, not completely. But everything else is pretty much not working at all. And that is what REM sleep looks like. And again, this appears to be your dream state. Because when you wake up somebody during REM sleep, they report dreams. When you wake them up during non-REM sleep, they don't report dreams. So again, REM appears to be your dream state. This appears to be your dream state. This also appears to be the most important portion of sleep in terms of your overall health. And that's, if you are sleep deprived, you will go into this REM sleep very rapidly. Under normal circumstances, it takes an hour or so to get down into REM sleep. But if you're sleep deprived, you'll go there really quickly within 10 minutes or so. And again, if we wake you up every time your eyes start to move, you don't get the benefits of sleep. You don't actually get the benefits of sleep. So REM appears to be the important portion of sleep. Why that is important, we don't know. There's a lot about sleep we don't know. The rest of the time, you are in what is called non-REM sleep. And there are actually three distinct stages of non-REM sleep that we can see based on looking at the EEG. But during non-REM sleep, we start out in those light theta waves, and then we slowly drop down into those deep delta waves. So again, as you're lying in bed, getting ready to fall asleep, you've got these nice alpha waves, then you fall asleep and you dump here into the theta waves, and you continue dropping down until you get into these nice, long, slow delta waves as you continue to sleep. And as you get deeper and deeper into sleep, your vital signs drop. Your heart rate, your breathing rate, your body temperature all go down. And become very regular. They become very, very regular. So during deep sleep, everything is turned off, and it becomes very, very stable. And again, your breathing and heart rate are very regular during non-REM sleep. The deepest stage here is stage 3. That's your slow delta wave sleep. And this appears to be when you consolidate your memory.
Bless you.
Memory consolidation appears to occur during delta wave sleep. So again, memory consolidation appears to occur during delta wave sleep. So again, but we undergo various sleep cycles as we sleep. So as you're getting ready to go to bed, you hop in bed, you fall asleep, and you fairly rapidly transition down into that deep sleep state. You stay there for a while, and then you rapidly come back up into REM state. Stay there for 20 minutes or so, drop back down. Go back up, drop back down, multiple times a night. And these are known as sleep cycles. So again, upon first falling asleep, you go into that theta wave sleep, that non-REM sleep, and over a period of half an hour, 45 minutes, you drop down into that non-REM, that deep delta wave sleep. Again, it does take some time to do that. You'll stay there for a while, and then you rapidly go back up, and you'll have a dream state. Then you drop back down again. And again, you go back down again, spend some time there, go back up again. And you'll do this over and over. Typically, people go through 4 or 5 sleep cycles a night. And each cycle takes between an hour and a half. 90 hour and a half, roughly, to complete the sleep cycle. Again, we go through 4 or 5 of them a night, multiply that out, it's about 8 hours. But you'll notice here, as we take a look at these sleep cycles, they're not all the same. The sleep cycles are not all the same. Initially, you will drop down pretty quickly, and you go very deeply into sleep. Later on, towards morning, you don't get into that deep delta sleep anymore. And your dream states get longer. Your dream states get, your REM sleep gets longer. So again, we cycle through these multiple times every night. And again, it's the whole cycle. Again, most of us require about 8 hours of sleep a night. It is highly variable from one person to the next. Yes.
Why would you think that the most highly functioning people on the planet sleep the least? Because it doesn't seem to make a lot of sense. Because if I slept for like 5 hours.
I don't know if that's actually true. The only people you ever hear about how little they sleep are the people who are really good at things. You don't hear about the other people who will also maybe just as talented who are sleeping 10 hours a day. Because they don't brag about it.
Okay.
There is a cultural bias to brag about how little sleep you can get away with. So I don't know if anyone's actually studied that one to actually say that's actually true. But I don't know if it's actually true, yes.
So I actually perform way better on 4 to 5 hours of sleep a night, and then if I sleep more than like 7, I'm exhausted the whole day.
Okay. By the way, it does not have to be 8 hours straight sleep. I do not sleep the entire night through. I will wake up in the middle of the night a couple of times. I'm pretty sure I wake up between sleep cycles. And then I just fall back asleep. And that is pretty common. That's pretty common for people not sleep throughout the entire day. Some people sleep 6 hours a night and then take a 2-hour nap in the middle of the afternoon. And again, this is highly variable from one person to the next. As long as you're getting sufficient sleep, you're fine. By the way, you cannot oversleep. You will not oversleep if you're not actually tired. You will wake up when you have sufficient sleep, and that's it. I can tell who out there has not gotten enough sleep because we're ones who are falling asleep on me. If you are just bored, you don't fall asleep, you just stare at the ceiling. And again, I see that too, by the way. But anyway, I pay attention to the way people are going to go there. But anyway, it's highly personal. How we sleep, different people sleep at different amounts. By the way, all animals do this. All animals do this. Dogs have REM sleep as well. We don't know if they're actually dreaming or not because they can't tell us. But any animals that we've looked at, we see these things occurring. And again, the amount of sleep that you need is variable. We say 8 hours. Some people work just fine on 6 hours. Other people are very cranky if they don't get 10 hours. So again, it is highly variable from person to person. So, why do we do this? Why do we spend a third of our lives asleep? Short answer is, we don't know. But we do know you absolutely have to do it. It is absolutely essential that you sleep. And again, it appears to be the REM sleep that is most important. But again, we don't know why. We really don't know why it is so important. But we do know your REM sleep, that is when dreaming occurs. And if you don't get enough REM sleep, first of all, you get very cranky. then you go mad, and then you die. If you keep somebody up for more than a few days, they literally go crazy. They literally become psychotic. Keep keeping them up, and they will die. And again, this is no, yes.
They had those one contest where you would do like,
Mhm.
they'd have a car and you'd have to keep your hand on it.
Yep,
And some of the people would start to hallucinate towards the end of it.
yep, exactly. Because believe it or not, sleep is important. Yeah, the record for going without sleep is actually pretty long. And by the way, if you go without sleep for a long enough period of time, it causes permanent brain damage. By the way, sleep deprivation is considered torture by the Geneva Conference. So if you don't want to be accused of war crimes, don't sleep deprive your prisoners of war. Yes.
Where does like sleepwalking come in? Does it have
That's a
any?
whole different issue.
Okay.
That's during REM sleep, everything's supposed to be turned off. It's not turned off, and you're active, and you're basically acting out your dream. I think. Again, I'm not an expert on this. Go talk to a psychologist. They can give you more insights into how that actually works. But again, if you don't get enough REM sleep, we do know that after a while you will actually see permanent brain damage and death. And it is the REM sleep because they've done experiments where they wake them up as soon as seeing the eyes move. The non-REM sleep is good, but doesn't give you the benefits of sleep that REM does. Doesn't give you those same benefits. All right. So again, why? We don't know. What is that non-REM sleep all about? Well, it appears to be when we consolidate our memories. So during that deep delta wave sleep, that appears to be when we consolidate our memories. And again, it does take a half hour to get down into that deep delta wave sleep. So if you're going to take a nap, you should probably give yourself back an hour to consolidate your memories. But anyway, it also has been proposed that it's used to repair free radical damage. Again, this is not proven at this point in any sense of the word, but we do repair free radical damage at some point, so this may be when we're doing it. So what is free radical damage? What's a free radical? A free radical is an unpaired oxygen. Oxygen is a very highly reactive element. It will bind to anything it can get its hands on. So oxygen is likely to bind to just about anything. So if it's not bound to something, it will find something to bind to. And that is what free radical damage is. It's oxygen binding where it shouldn't to things like DNA and proteins. And disrupt the way that they're working. This is what antioxidants do. They bind oxygen. Antioxidants are there to bind up these free radicals. Because if you don't, it causes damage. We are producing these free radicals all the time. Every time we run through the Krebs cycle, you're producing them. So we're producing these free radicals all the time. We have antioxidants inside of us to try and bind them up so that it doesn't cause actual damage to us. But we do get damage from these things, and it does need to be repaired, and it is thought that this occurs while we're sleeping. One of the things that happens is that we do this while we're asleep. Again, not a lot of evidence for it, but it happens at some point, so we might as well do all the rest of it, I guess. Any event, that's why we sleep. The exact reasoning behind any of this, unknown. But all animals sleep. Dogs, cats, fish, they all sleep. Worms sleep. Anything we've ever looked at in the animal kingdom sleeps. Spends part of their life asleep. By the way, whales and dolphins, half their brain sleeps at a time, so they can keep swimming. Because if they don't, they drown. They're literally half asleep. Any event, that's sleep. And that's a little bit about the autonomic system, things that are going on in the background. Any questions before we move on to sensations? All right, so for the rest of the semester, which is only 2 more lectures after today, we will be talking about, yes, 2 more. we'll be talking about the sensations. And the sensations are perception of external stimuli. So in other words, how your brain knows what's going on outside. So when we're talking about the sensations, we're talking about the perception of external stimuli, something happening outside and you finding out about it. It's how your brain knows what's going on around you. And we have a lot of different sensations available to us, and they have some things in common, they have some things that are not in common. But among the things that are in common, they all have to have some sort of a receptor out there that picks up that stimulus and sends it into the brain. And the brain, what it sees are the neural impulses coming from that receptor, initiated by that receptor at least. Your brain only sees information coming through the neurons. So everything out there has to be transduced or converted into a series of neural impulses. In other words, a firing rate of action potentials. So when we're talking about sensations, what your brain is seeing is changes in how the axons are firing off, either faster or slower. And it then needs to interpret what all that actually means. But the brain only sees a series of neural impulses. It only sees action potentials. It doesn't see light, it doesn't see heat, it sees those neural impulses that are reporting changes in light and heat. Differences in perception are due to differences in these neural impulses, or rather the pattern of those neural impulses, because the action potentials are always the same. So again, in some cases we're going to speed it up, that says, hey, there's something out there. In other cases we're going to turn things down and say, hey, there's something out there. But again, it's always, bear in mind, we're always talking something mediated by neurons. All your brain sees is the action potentials coming from the neurons. And whatever provokes those action potentials will be perceived as that sensation. So if you take a photoreceptor in the eye, shine light on it, your brain says, hey, there's light out there. If instead of shining light on it, you were to electrically stimulate it, use an electrode, your brain would say, hey, there's light out there. Your brain only sees that neural impulse. That's all it can go by. So it's always going to report it as if it were the sensation that it's supposed to be reporting. So again, your brain only knows those neural impulses. Regardless of what actually caused that, you could have chemically stimulated or something along those lines, your brain's still going to interpret it as if it was what it was supposed to be. That's the unitary hypothesis. So again, regardless of what the stimulus actually is, your brain is going to interpret it as if it is a normal stimulus. So again, anything that activates a photoreceptor will be perceived as light. Anything that activates a olfactory receptor will be perceived as smell. All right. And to get these in, one more, adaptation. All of your senses, by the way, adapt. What do I mean by that? Over time, you stop paying attention to them. Adaptation is the loss of sensation with continued stimulation. So again, an example of this would be if I were to take an onion, cut it open, you would all smell onion pretty rapidly. 10 minutes later, would you still be smelling that onion? Let's say 15 minutes later. Not really. Does that mean those onion particles are no longer in the air? No, they're still there, you're just not paying attention to it anymore. That's adaptation. All sensations adapt to some degree. Some, like your sense of smell, adapt pretty quickly. Others, like your sense of sight, adapt very slowly. I can stand here and stare at that brick wall for a long time and I'll still see a brick wall there. But if I stare at it long enough, it will eventually disappear. Not that I'll be able to see through it, I'll just stop seeing that. But again, sensations all adapt to some degree, some faster, some slower. And again, there's all sorts of optical illusions you can see on that will actually demonstrate this. But anyway, all sensations adapt to some degree. And when we're looking at sensations, they all follow a similar pathway. Number one, there has to be a receptor for it. If you don't have a receptor for it, you can't sense it. We don't see UV radiation because we don't have a UV sensor. By the way, rattlesnakes can see in the infrared. They have an infrared sensor, a heat sensor. We don't. But again, different animals have different sensors out there and can see different things. But again, you need to have something that picks it up. If you don't pick it up, you don't know what it is. And then it needs to take that stimulus and change it into a pattern of neural impulses, which then need to be conducted into the central nervous system by a neuron. So again, you're going to have a receptor out there that's going to do something and stimulate a neuron to take it into the central nervous system. Then the brain needs to look at that signal and tell you what it is. It needs to process and then interpret what the signal actually is. All three of these must be functional for that sensation to occur. Take out any one of them, and you do not get the sensation. If you block a receptor, you don't see the change in neural stimulation. If you break the neuron, the information doesn't get into the brain. If the brain doesn't know what to do with it, it doesn't know what to do with it, and you don't get the sensation. All three of these things will be present for all of our senses. Now, when we're talking about those sensory receptors, there are a variety of different kinds of sensors we can have out there, receptors. Some of them are said to be simple neuroreceptors, in which case you have a bare nerve ending hanging out someplace in the body and picking up whatever that is. Your sense of smell uses a simple neural receptor. Odorants, chemicals that can smell, bind to that neuron and produce an action potential and carries it into the brain. That is a simple neural receptor. Many of your touch receptors, things like itch and tickle and temperature, are bare nerve endings. By the way, when we're talking about bare nerve endings, what are we talking about in terms of the structure of the neuron? Yes?
The axon terminals, dendrites?
Dendrites. I was going to say the other end. It's the dendrites. These are dendrites. These are dendrites with some sort of a receptor out there. Then we have what are called complex neural receptors, in which case we take that bare ending and we put a cap on it. We put some sort of a cap on it. We've seen these before when we were looking at the skin. We saw the Pacinian corpuscles, we saw the Meissner corpuscles. Those are complex neural receptors. They have some sort of connective tissue cap on the end of the neuron. And when the cap gets moved around, it causes the neuron to respond. So those are complex neural or encapsulated nerve endings. That capsule is typically called a corpuscle, by the way. And then we have specialized receptor cells. We have photoreceptors in the eye that pick up photons. We have hair cells in the ear that pick up sound waves. These are specialized receptor cells. They detect whatever happens to be out there and then release a neurotransmitter to the neuron that then carries it in. So we have specialized receptor cells. Again, we have different sensations: vision, hearing, balance, taste. All use specialized receptor cells. All right. Now, when it comes to sensing, there are a number of different things that we can sense. First of all, we have what are called chemoreceptors. Chemoreceptors detect specific chemicals in the environment. Taste, smell are chemoreceptors. A lot of our pain receptors are chemoreceptors. They detect specific chemicals hanging around out there and report it back. They detect specific chemicals. We have photoreceptors that detect photons. Photons are particles of light. So photoreceptors detect light. We have thermoreceptors that detect changes in temperature. We have hot receptors, we have cold receptors. We have two different sets there, by the way. Some respond to increases in heat, others respond to decreases in heat. We have mechanoreceptors. Your sense of hearing uses a mechanoreceptor and uses movement to detect it. Your pain receptors, a lot of these, if you pinch yourself, that is a mechanoreceptor. So again, much of your sense of touch, those are mechanoreceptors, picking those up as well. So they detect some sort of a movement. Nociceptors detect tissue damage. These are your pain receptors. Either by binding to a chemical that is being released by that damaged tissue or some sort of mechanical deformation. Again, nociceptors are your pain receptors. And they detect damage and produce pain. So again, we have a number of different kinds of receptors out there. And when it comes to the senses, we divide them into two broad groups. We have what are called the cutaneous or the general sensations. Cutaneous because for the most part the receptors are in your skin. General because they occur throughout the entire body. These include things like touch, temperature, itch, tickle. These are pain. Those are all general sensations. They occur throughout the entire body. It doesn't matter if I take an ice cube. It doesn't matter where I touch you. You will feel it is cold. They're distributed around the entire body and include things like touch, pressure, hot, cold, pain. These are all cutaneous sensations. And then we have what are called these special senses. The special senses are mediated by specific organs that in humans all happen to be in our heads. And these include smell, taste, hearing, sight, and the vestibular sense. The bottom one here, the vestibular sense, that's your gravity detector. That tells you which way is up and down. That is one of those that's your sense of balance. That's your balance. That's one of those sensations that's so basic that people didn't recognize it was actually a sensation for a while. But if you lose it, you're very aware that this is something you need to do. So again, we have both cutaneous and special senses. We're going to start with the general sensations. And all the general sensations, we've actually seen this figure before, go onto the post-central gyrus of the parietal. They all match onto the post-central gyrus. So if I touch you on your toes, you'll feel it over here. If I touch you on your face, you'll feel it over here. And as a general rule, it maps to the opposite side of the brain. So anything going on with your left hand will map onto the right side of the brain. Anything from the right side of the body will map onto the left side of the brain. So everything crosses on its way over. But again, we generally going to get information from the contralateral side, projecting up here into the brain. So again, the post-central gyrus is where these all map to. And they're mediated by a number of specific receptors. And you can see a variety of them hanging out in here. We have some that are very endings. Here's a Pacinian corpuscle, that's a monocer corpuscle. And there are other forms hanging out here as well that we'll talk about a little bit later on. But there are a lot of different kinds of receptors hanging out in the skin, and they're located all over the place. And each of these receptors has surrounding it what is known as a receptive field. The receptive field, that's the area of the skin that is monitored by that one receptor. The smaller the receptive field, the better the localization. So if you want to know where something is, here we have a receptor here, and it has some receptive field around it. If I touch anywhere within this receptive field, it will be picked up by that receptor. But it can't tell if I'm touching here or if I'm touching over here. Again, that receptive field just says there's something happening inside of it. If I have a much smaller receptive field, I have a lot better localization. I can say exactly where this is a lot better because it's a much smaller receptive field. So if I touch here, I'm not going to be picking up, but if I touch here, I will. So I only have this area here that will be picked up by that one. And these receptive fields all have a tendency to overlap one another. They have a tendency to overlap one another, which will give me even better discrimination as to where something is actually located, using what is known as lateral inhibition. So what is lateral inhibition all about? Well, it says that if I touch here, this one's picking it up, this one isn't, I can subtract that. I can subtract those regions of overlap. And that is known as lateral inhibition. And it's all dependent on the fact that the receptor fields overlap. This, by the way, occurs in the brain. This is not something happening on the skin, this is something that's happening in the brain. Because we have the fields are overlapping, we end up with sharper definition of the stimulus location by inhibiting the ones that are not being activated. By turning them off and saying it's not there. Yes. So most strongly stimulated receptor field inhibits the sensation from the neighboring fields, which gives us, in other words, we're subtracting what the overlap regions. And again, this is something that's occurring in the brain and the spinal cord. This is not something happening out in the taking all that information coming in and processing it and giving us a much better idea of exactly where it is something is actually touching the plant. And that is known as lateral inhibition. All right, so again, we have a variety of different kinds of receptors hanging out in our skin. Some of them are free nerve endings. So some of the sensations out in the skin, these are free nerve endings, and these include things like itch, tickle, hot, cold. These are all free nerve endings. Note here, by the way, hot and cold are two different things. Hot and cold are separate. Pain receptors are bare nerve endings. And we're just going to see a nerve ending hanging out in your skin somewhere, picking up all these different things. And by the way, you do have specific itch and tickle receptors. You do have specific receptors for those sensations. The hair root plexus that you all remember from when we talked about the skin, that's that nerve that wraps around the hair follicle, is also a bare nerve ending. Again, anything that causes the hair to move here will be picked up by this bare nerve ending wrapped around that hair plexus, around that hair follicle. So those are all free nerve endings. Then we have a variety of encapsulated nerve endings as well. Some of these we've already seen. This is what is known as a microcorpuscle. They tend to be up here, up in the dermal papillae, and they measure a form of light touch. Your book is calling these tactile corpuscles. I don't like that term. Tactile just means touch. These are all touch receptors. But these microcorpuscles are hanging out in the dermal papillae, close to the surface of the skin, and they're measuring a light form of touch, something just sort of brushing against you form of touch. Then we have what are called vertical discs because they're disc shaped. These are vertical discs hanging out over here. They measure a more sustained form of touch, a slowly adapting form of touch. So the Merkle discs, those are rapidly adapting. You put your clothes on in the morning, you feel them going on, and are you now still feeling them? No, you quit feeling them pretty quickly. The Merkle discs, they will continue feeling it for a longer period of time. They are slowly adapting. So a more sustained form of a light touch. Deeper in, we have what are called lamellated or Pacinian corpuscles, and they measure a deeper form of touch, something pushing against you kind of touch, or a pressure. They're really good at picking up vibration as well. They're really good at picking up vibration. Again, these are rapidly adapting. As you sat down, you felt the pressure from the chair pushing up against you, and then you immediately stopped paying attention to it anymore. This one over here is what is called a Rubini corpuscle. They have an elongated appearance to them, and they are good at detecting stretch of the skin. These are more slowly adapting again, so they will retain and feel that stretch for a fairly long period of time. But these are different kinds of cutaneous receptors, and there are others. And that's all I'm going to tell you about the general sensations. Next time we'll go ahead and talk about the special senses. And hopefully we'll get through that. You might want to look ahead on these, because again, we only have a week left. And again, we will not get to the ear until next Monday. So you might want to take a look at that.
Are the cats gonna be out, at some point so we can,
You
like,
can get the
go to
cat.
the,
You can get your cat,
okay, like after lab on Monday?
well, you didn't know
Okay.
that.
You can get the cat out anytime.
Again, open labs will end after.